I will explain about the interaction of this experiment in the study of understanding how establish three experimental benchmarks to ensure quantitative accuracy and precision. Just a home glucometer utilizes internal calibration mathematics to match standard laboratory blood plasma benchmark. The food industry relies on standard chemical benchmark to evaluate raw materials and final product. This experiment applies principle of volumetric analysis to quantify the titrable acidity of commercial orange juice sample.
So I'll be talking about the theory. So the first theory is the reaction between acid citric and also sodium hydroxide. So as we all know, in this experiment, we will be using acid citric, which is a type of weak organic acid, which they partially ionize when in contact with water, and also the sodium hydroxide, which is a type of strong base, which they are fully ionized when in contact with water. So the balance equation is C3H5OCOOH3, which is aqueous, react with 3 sodium hydroxide aqueous, which results in creating C3H5OCOONA3, which is aqueous, and also 3 water, which is liquid. So citric acid is a triprotic acid, which meaning it requires 3 molecules of NaOH, which is sodium hydroxide, to completely neutralize 1 molecule of citric acid. So the second theory is the endpoint detection theory. So titration complete when it reaches to the endpoint, but how do we know that it already reaches the endpoint? So when the solution in the conical flask change from colorless or any color into faint pink color, which is due to the phenolphthalein reaction, for at least 30 seconds. So why do we use phenolphthalein? Because it has a suitable pH range, which it changes color in pH range between 8.2 to 10. So it also due to its accuracy, which phenolphtalene's colors transaction range from 8.2 to 10 perfectly brackets this equivalent point, which is 7, which is 7 is between 8.2 and also 10, and it serves as an incredible accurate visual marker that the reaction is complete. So for the third theory, which is the calculation of titratable acidity, the calculation is derived from the molar ratio of balance equation, which I already explained before this, which 3 mole of sodium hydroxide is equals to 1 mole of citric acid, and we calculate it by using the formula Ma times Va over Mb times Vb equals to 1 over 3, and to calculate the percentage of citric acid in the sample, we use the formula percentage citric acid is equals to Mb times Vb times equivalent weight of citric acid over V sample times 10 times 100%. So Mb, which refers to the molarity of sodium hydroxide, and Vb refers to the average volume of sodium hydroxide used, and V sample refers to the volume of orange juice which we pipette. For the fourth theory, which is the error during experiment, there are 2 types of error which is likely to occur during the experiment, which the first one is the systematic error and the second one is the random error. So for systematic error, it is most likely that the natural yellow or orange pigment of the juice makes it difficult for human eye to perceive the initial reading, and there might be a or the subtle shift to faint pink, which might lead to over titration. And the second error, which is the random error, it is most likely that the misreading of liquid meniscus of the burette or pipette will happen, and also the uneven or weak swelling of conical flask, which might cause localized pockets of excess sodium hydroxide, which cause delayed color change.
Objective of this experiment: first, to determine the acidity of food product using acid-base titration, to apply acid-base titration technique for quantitative chemical analysis. 3. To calculate the concentration of acid present in the food sample based on the titration data. The chemical used in this experiment are orange juice sample, 0.1 molar sodium hydroxide solution, phenolphthalein indicator, distilled water, and the apparatus that used in this experiment are burette 50 ml, pipette 10 ml, conical flask 250 ml, beaker, funnel, and white tile. Drill procedure: first, a clean burette was rinsed and filled with 0.1 m NaOH solution. Step 2, using a pipette, 10 ml of fruit juice was transferred into the conical flask. 3. Approximately 20 ml of distilled water was added to the sample. 4. 2 to 3 drops of phenolphthalein indicator were added. 5. The sample was titrated with NOH with swirling continuously. 6. The endpoint was reached when a faint pink color persists for 30 seconds. 7. The final burette reading was recorded. 8. The titration was repeated 3 times to obtain consistent result. And the last step, the average titrate value was calculated and used to determine the titrable acidity of fruit juice.
Now we talk about discussion. This experiment successfully demonstrates the application of acid-base titration of food manufacturing. The variant quantitative technique used by quality control laboratory to ensure product consistency, flavor profile, and regulatory compliance. In industrial and food processing, the total titratable acidity of fruit juice is traditionally analyzed and present in terms of the product dominant and organic acid. Here, citric acid serves as the primary analyte. As a therapeutic acid containing in reactive carboxylic acid fraction group, it donates 3 hydrogen ions per molecule. It reacts with the hydrogen hydroxide titrate and in base 3:1:3 a substitute ratio according to neutralization equation, where a benevolent indicator marks the complete neutralization of this 3 acidic site by turning a faint resistant ring. For a manufacturing standpoint, sample inhibit a molar concentration of 0.18 molar and the mass and percentage of 0.352% acidic acid. In contrast, sample B inhibited with 0.19 molar and 0.3142 citric acid. Concentracy sample A a more sour juice because it higher mass percentage and larger volume of neutralization citric. Physically confirm a higher concentration of free hydrogen and ion. A minor calculation evasion visit in the data table. For example, feature a slightly higher recorded molarity display consuming less base volume. High manufacturing equation was maintained across both samples, particularly sample A identical and 55 ml volume across a 3 trial. Minor deviation of the absolute theoretical value can be attributed to standard laboratory limitation such as parallel reading error, the track presence of a neutral organic acid, or visual endpoint masking due to the reduced natural pigment. For the conclusion, the experiment successfully utilized acid-base titration to quantify the titrable acidity of an orange juice sample. By repeating the titration 3 times, a consistent average titrate value was recorded, achieving the high precision required by analytical standard. To ensure true accuracy, the experiment evaluated 2 main error types that can skew results. First, systematic error. Faulty equipment calibration, reading the burette at incorrect eye level, or using degrade juice stripe can create a consistent risk. Secondly, random error. Unpredictable factors like sudden room temperature shift or microscopic food residue or contamination on the skin or glassware cause random data spike. Managing this chemical error allows industry manufacturers to transition from manual or automated system, guaranteeing that every food product on the shelf is uniform, high quality, and completely safe.